Hello, welcome back to another episode of Math with Cause. You're watching Precalculus Season 2, Episode 20. We're continuing our investigation of trigonometry, and in particular, we're continuing looking at the inverse trig functions. In the previous episode, we looked at the inverse cosine function, and now we're going to look at the inverse sine function. So, just to kind of recap, the basic problem we have is something like this. If we are given y equals sine x, and if we want to get the x by itself here, then what we have to do is figure out a way of undoing the sine. And how we want to do that is using what's called the inverse function. So in this case, x is the input and y is the output, and that for the inverse sine function, the x is going to become the output and the y is now going to become the input. So the independent variable for the sine function is the x and the dependent variable is the y, and that is swapped here. So this is for the inverse sine function. So this right here is the definition of the inverse sine function. Now we need to talk about notation. So the traditional common notation you'll see today is this right here. And we must note that the -1 here is not an exponent. What this is referring to is the fact that we are talking about inverse functions. So this says the inverse sine function. And there's a better notation, or I should say a better way of saying inverse sine function instead of just saying inverse sine function. There's the old school notation, which is arcsine of x. So arcsine. So linguistically, I'm going to say arcsine. Notationally, I'm going to use this right here with this -1. Just remember it's not an exponent. It's referring instead to the fact that we're talking about the inverse sine function. So with that, we can continue. In the previous video, I do develop these ideas a little bit more than I do here. So this video is more so for those who've watched the previous one and not want to continue. So I just want to throw that out there in case you feel like there might be some holes. Definitely feel free to check out episode 19, and I will link that video down below in the description. Alright, so what we need to do is come up with a table of values. So if we have y is equal to sine x, we want to figure out what happens with arcsine. So actually, what I want to do is make a table and not have the equal sign here. Here we go. So we know that if we plug in 0 pi in for x, sine of 0 is 0. So our output is 0. If I plug in, say, pi over 4 into sine, we know we get out a square root 2 over 2. If I plug in, say, pi over 2, we know we get out a 1. Now, for arcsine, so there we go. So in this case, our output here is the 0 from normal sine, so that becomes our input. If I plug in 0, then I'm going to get out 0 pi. If I plug in square root 2 over 2, then I'm going to get out the pi over 4. So just like last time, when we have our normal sine function, we plug in our angle and we get out the square root 2 over 2. Now what's happening is for the inverse sine function, for arcsine, we are plugging in the output and we are getting out the angle. So notice our y coordinate, right? Because if we remember, Sine gives out the y-coordinate of the points on the unit circle. The pi over 4 is the angle. So we're plugging in the y-coordinate and we're getting out the angle. That's how the arcsine function works. So when we plug in a 1 in for x for arcsine, we are going to get out this pi over 2. And we can keep generating our table here. If I plug in, say, pi, that's 0, pi, 3 pi over 2, that's negative 1. So if I plug in negative 1, that's 3 pi over 2. 2 pi gives out a 0. So if I plug in 0, we get out 2 pi. And notice we get the same problem as last time. Notice 0 pi, pi, 2 pi. We have the same input, the same x value, but we get out a different y value. So just like with arccosine, for every single input value, there's actually going to be an infinite number of y values associated with it. And the reason, again, is because when you think about just y equals sine x, right? For any angle, you can find a coterminal angle just by adding or subtracting a quantity of 2 pi. So every x and y coordinate on the unit circle is going to be associated with an infinite number of angles. And so when you have as your input those x or y coordinates, you will get an infinite number of possible outputs. And so just like with the cosine, with arcsine here, we will have to restrict the domain, or not the domain. That's kind of funny. In both videos now I've accidentally said domain when I meant the range. So to see visually what's going on more, let's go ahead and start graphing. Alright. So we are graphing the inverse sine function, and the odds are we will need more room than what I gave myself. So if I plug in 0 in for x, we know we get out 0, so here's our first point. So just to note, we are only looking, we are looking at only the right side here. So the left side of the graph was only, or our chart here was only for helping generate the right side. Now we're graphing the right side to see how arcsine behaves. So here's 1, here's negative 1. Note that square root 2 over 2 is about 0.7. So here's pi over 4. 1.7 is about there. If I plug in 1, I get out a pi over 2. So there's that. And then up here at pi, we're at 0. So here's this. It's a terrible looking graph. If I plug in 3 pi over 2, so yep, notice we're already not enough room. 3 pi, oops, we don't want to point there. We want to point out here at negative 1. And then 2 pi, we're back at 0. Alright, there we go. So we get this kind of wavy pattern, and we'll bring up our Desmos graph and we can verify. See, nice wavy pattern. And just as I mentioned before, this is going to go on for infinity, right? All the angles are our outputs, and there's an infinite number of angles associated with every single value between negative 1 and 1. So for example, if we graph x equals a half, we have all these different angles associated with that, and these are all the coterminal angles associated with pi over 6 and 5 pi over 6. Alright, so just like we talked about before, this causes a problem. when we think about the vertical line test. Vertical line test says if you draw a vertical line, if that line intersects your curve at more than one place, then it cannot be a function. So we have to restrict the range. So how we're going to restrict the range is we're going to pay attention to the values between down here and up here. Okay? So this part here in black, that is going to be the range of arcsine. Okay. So when we think about the fact that 0, pi, pi, and 2 pi all give you 0, what we did was restrict the domain in a manner so that we don't run into this problem several zeros. So if we try to make our range similar like with arccosine, so if we want to go from like 0 to pi, notice we would be getting 2 of everything, right? Every single value that we plug in, we get out 2 values. So even though for arccosine we had a range from 0 to pi, that's not going to work here, because if we considered all the values between 0 and pi, right, or that's the part right here. So now we need the other half. So if we go think of negative angles down to negative pi over 2, that will give us the bottom half here. So to go to the unit circle, what we are essentially going to use for our range, we're going to take all the angles going up this way starting from the positive x-axis, and we're going to take all the angles over here starting from the positive x-axis, and we're going to go clockwise and counterclockwise. And so all of the possible angles that arcsine can give out as output is going to be on the right side of the unit circle. So just kind of recap. Here's sine x, here's arcsine x. Domain, range. So we mentioned that the range is going to be restricted from negative pi over 2, pi over 2. This is to ensure that for every single input, every single x, that we get out only one angle, right? So that's where this range is coming from. Now when we think about sine and its domain and range, sine had a domain of all real numbers, but the range was values between negative 1 and 1 because we're on the unit circle and you can't have a radius greater than 1. So since the range for sine is from negative 1 to 1, when we think about arcsine as the inverse sine function, the outputs now become the inputs, and so we saw that the domain is actually going to be from negative 1 to 1. And looking at our graph here for Desmos, we certainly see that. Right? If we scroll out, every single output or possible input values between negative 1 and 1. Right? If we considered the graph with the infinite squiggle here, it doesn't go outside of this domain. So this right here is the domain and range of arcsine. Domain to a negative 1, 1 ranges from negative pi over 2 to pi over 2. Visually speaking, the range of arcsine is the right half of the graph. And if we wanted to arccosine, to recall from before, arccosine was the top half. Okay, so arccosine had the domain up from pi or 0 to pi. So y equals arccosine x was from 0 to pi. Alright. And with that, we can conclude our discussion about arcsine. Alright, if you've been enjoying our content, please subscribe to our video or our channel. Your support is greatly appreciated. Also consider supporting us on Patreon. By supporting us on Patreon, you can get some cool perks, and you can help me out with future projects on allocating new resources for our new series. Such as one thing I do want to dive into more is kind of the history and philosophy behind mathematics, and to do that requires some more research, and that research requires money. So if you have been enjoying our content and want to continue supporting us in new ways, consider Patreon. Otherwise, please continue watching our videos. Thank you for watching this one. Thank you for joining our math party, and I will see you next time, and we will look at the inverse tangent function.